All right. Welcome to the DDPS seminar, everyone. Before we start, let's go over some rules and logistics. First of all, please mute yourself during the talk unless you have questions. If you have questions, you are welcome to unmute and ask. Otherwise, please use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. No classified discussion is allowed, so please watch out. Finally, the talk today will be recorded and uploaded in LLNL YouTube channel. That's about it. Now let me introduce our speaker today. It is an honor to host Marta D'Elia, who is a principal member of the technical staff at Sandia National Laboratories, actually across the street from us, where she works since 2014. She is currently part of the computational science and analysis group at the California site. She obtained her master's degree in mathematical engineering at Politecnico of Milano under the supervision of Professor Quattroni. She obtained her PhD in applied mathematics at Emory University under the supervision of Professor Veneziani. Here, she worked on optimal control in CFD for cardiovascular applications. She was a postdoctoral fellow at Florida State University, where she worked with Professor Gunsberger on optimization for non-local and fractional models. She's an associate editor of CISC and CA, Advances in Continuous and Discrete Models, and of the Journal of Paridynamics and Non-Local Models. Her interests include non-local modeling and simulation, optimization and optimal control, and scientific machine learning. Today, Marta will talk about data-driven learning of non-local models, reaching scales and design of new neural networks, which is very interesting topic. Please enjoy and expect a wonderful talk. Now, without further ado, let me pass the baton to Marta by asking one random question as usual. Today's random question is, what would you rather throw away, either love or money?
Say it again, what
would you rather throw away, love or money?
Oh, money.
Oh, okay.
Certainly.
Of course, right?
Yes.
Okay, thank you, Marta. It's all yours.
Thanks a lot. Thanks a lot for having me. Thanks for introducing me. It's really a pleasure to present in this seminar series. As it was mentioned, this talk is going to be about data-driven learning techniques for non-local equations. The research that you're going to see today is partially supported by the LDRD program at Sandia and by FILMS, which stands for Physics Informed Learning Machines, and is DOE Asker Mimics Center, PI'd by George Karniadakis. This is a brief outline of my talk. It's going to be organized in two parts. First, I will introduce an operator learning algorithm for non-local equations that we're going to use to address challenges in homogenization. And in particular, I will focus on designing optimal surrogates for molecular dynamics displacements. Then there's going to be a second part where some of the tools that were introduced in the first part are going to be used to design optimal architectures for for neural networks, and we're going to refer to these as non-local kernel networks. I will start by summarizing the properties that we're after, and then I will show non-local kernel networks in action with PDE-learning tasks and image classification tasks. These are the people that contributed to this talk. Stuart Sealing at Sandia Labs, New Mexico. Stuart is the father of paridynamics, the non-local theory for mechanics. Huaichen Yu and Yue Yu, they're both from Lehigh. Yue is the advisor of Huaichen. And Huaichen was, until a couple of weeks ago, a long-term intern at Sandia Labs, California. All right, so in the first part of my talk, I'm going to focus on complex systems where the small-scale dynamics, the small-scale interactions affect the global behavior. And these, of course, are ubiquitous in scientific and engineering applications. In particular, I'm going to focus on systems where the effects of heterogeneities at the small scales need to be captured accurately to have reliable predictions. So, of course, we can use, at the very small scale, we can use classical models such as PDEs and solve for those small scales or those small-scale heterogeneities and get accurate solutions. The problem is that these simulations are very expensive computationally and oftentimes cannot be afforded. And so there is the need for new upscaled models that act at larger scales, but can still capture the effects of small-scale behavior. The process of coarse graining or upscaling, however, hides several pitfalls, and these pitfalls may compromise the reliability of the models. In particular, when we have heterogeneities, we have that the homogenized model has to follow a different governing law and has to have a different constitutive property compared to the one that applies at a small scale. So what I'm reporting here on the right is a very simple example where we don't even have a super high degree of heterogeneity. This is kind of homogeneous sand. And what happens here is that a simple advection diffusion equation is accurate at the very small scale level, but as soon as we coarse grain, as soon as we look at things at a larger scale, a simple PDE is not enough anymore. And so we're facing a capability gap in some sense. So in the sense that homogenized classical models are in general not sufficient to fully reproduce coarse grain behavior. What we claim is that integral, and I will provide hopefully enough evidence to support this claim, integral operators or non-local operators can provide better descriptions than PDEs because they embed all the time and length scales in their definition. So what I have here is the simplest maybe example of an integral operator where the length scale is embedded in the domain of integration. So we have this neighborhood of radius delta. It doesn't have to be a Euclidean ball. It can be pretty much anything. And we refer to this delta as horizon or interaction radius. Of course, though, as any other mathematical model, integral operators depend on parameters. And these parameters are in general unknown. And more importantly, non-local operators, in non-local operators, we have that the constitutive laws take the form of kernels or integrand functions. And the form of these integrand functions cannot be established a priori. And it's hard, in some sense, to establish a connection between material properties or media properties and these functions. So today I'm going to focus on operators, mostly on operators of this form. These are known as non-local diffusion operators, or this is simply a non-local Laplacian. So from this formula, we see that the regularity assumptions on the solutions can be relaxed because there are no derivatives. So this is the non-local counterpart of a Laplacian, but once again, there are no derivatives. And so our solutions can be very nasty. They can be irregular. They just have to be integral in some cases. These operators depend on kernels, these kernels K. They're application dependent, and they determine the regularity properties of the solution. And as I said already, they're in general unknown. And this is one of the biggest challenges and open problems in non-local modeling. Now, this being said, non-local models have been successfully used in the literature. I mean, we have many success stories, the use of non-local operators. I'm going to mention one that is particularly relevant in this specific setting, which is homogenization. And it's the use of fractional operators. And I know that these operators have been mentioned in this seminar series already. So fractional operators can be used to model anomalous transport in the subsurface. And they're particularly effective in the presence of a very high degree of heterogeneity. You can recognize here, so here C is the concentration of a pollutant in the subsurface. This is the fractional counterpart of a classical Laplacian. And you can recognize the same structure that I had in my previous slide, and the kernel K in this case is this fractional term. So, and to show you an example of how effective these operators are, this is a paper that dates back in 2001 by Benson. And this is for the so-called May data set. It's a very, it's a highly heterogeneous data set. And the solid thick line is the solution of the fractional model. So it's called alpha stable. And it almost matches the data, the concentration data. And here at the bottom, the flat line is the standard PDE, the advection diffusion equation. So the difference is certainly striking in this case. So there are examples of where the kernel function is known and can be used, and it also has some sort of physical interpretation, I would say. However, we're interested in systems where the connection between the data that we have and the kernel is not that immediate. And so this is the recipe that we propose. Of course, I mean, there is no need for me to advertise the combination of machine learning and physical laws. We know that this is a winning strategy. What we want to add into the picture is, we call it unified calculus, and it's basically a calculus that includes the classical calculus, but also the integral calculus, so that we can give some, we can get some models that are mathematically rigorous. So what we're after are new non-local models or optimal non-local models that are guaranteed to be well posed because of the calculus and that are physically consistent. So our working assumption is that we can collect high fidelity data or perform small scale high fidelity simulations. In what you're gonna see next in the main topic of this first part, the high fidelity is gonna be molecular dynamics, but it can be DNS, or we may have exact solvers. And going back to what I said at the beginning, our goal is to find an optimal non-local model that at a larger scale basically reproduces the high fidelity model or is as close as possible to the high fidelity model. So the question, since we decided to describe this operator as the non-local Laplacian, the real goal is to find the optimal kernel K. So I'm going to start from basically the core technique that I'm going to use that was introduced last year in this paper, and then extended in two subsequent papers. I'm going to summarize this technique in 3 simple steps. And for now, I'm going to start from a scalar unknown, so from a scalar variable. This is, again, the operator that you saw at the beginning. K is our unknown, and we're interested in the elliptic equation, so in the non-local counterpart of a Poisson equation. Basically, this is the residual of the equation that we're looking at. We collect measurements. These are our high-fidelity pairs of solution and forcing function. And we build a surrogate for the kernel. In this specific case, so what we have here is a linear combination of basis functions. In our first work, we consider Bernstein polynomials. So this is the form of our kernel, which is uniquely determined by the coefficient Cm. And then we minimize the residual. So here's where the physics comes into play, subject to solvability constraints, or in other words, non-local theory that guarantees that this operator, once we learn K, is well posed. The outcome, of course, are the coefficients that uniquely determine the kernel. This was the first work that basically could learn the functional form of the kernel. Previous works were focused on learning parameters of given functional forms for the kernel. A very important feature of this algorithm is that we allow the kernel to be sign-changing. So first, let me say that whenever this kernel is positive, it's much easier to prove the well-posedness of the system associated with this operator. As soon as this kernel can take on negative values, the proof of well-posedness is more involved. However, there's evidence in the literature that sign-changing kernels are particularly effective in describing the high-frequency response of materials. So when we want to model material response, we'd better use a sign-changing kernel. And we then embedded in this algorithm some non-local theory developed by D'Elia, Mengesh, and Chandu that basically gave us some explicit sufficient conditions on the kernel to be sign-changing and to induce a well-posed problem. And so from now on, we always allow the kernel to be sign-changing, but we have to keep in mind that specific conditions for well-posedness need to be embedded. This is a first example of how we apply this operator learning technique. And I just have 2 slides. This is a simple extension of what I just presented. And we extend that to the vector case, basically. So now we're looking at elasticity. In particular, we're looking at elasticity in bodies whose microstructure is heterogeneous and is periodic. So this is a 1D example, this is a 2D example, and these are different types of microstructure that we considered. So the point is, while with the PDE, and in our case we use finite elements, we have to mesh the whole thing, we have to solve for these interfaces. When we use a non-local model, what we're going to do is to put 1 degree of freedom in each unit cell. So here we're just going to have 1 degree of freedom. And so based on some high fidelity measurements, which are going to come from fine grid finite element simulations of the linear elasticity equation, we want to learn the best kernel K such that this model describes well enough the material behavior. So now the other yes.
So sorry to interrupt, but there's a Firefox icon and the camera icon, and it's blocking.
Yeah,
you know, some of
I cannot.
Is there a way?
I'm not sure I can move it. Oh yes, I can move it. Okay, it's on my name. Wonderful. You know who I am. Is it better?
Yeah.
Great.
That's better.
Yes, I apologize. I thought you were not able to see it, but okay. So the other extension that we have here is the second derivative in time. So now we have a hyperbolic equation. But the algorithm is exactly the same. So we still minimize the residual of the equation. In this case, and this is something that we learned in the subsequent papers, it's very important to add anything we know about the physics. And in this particular case, I'm not going to focus too much on this example because I want to focus more on the molecular dynamics case. Here we added a constraint on the second moment of the kernel. As I already said, the high fidelity is given by a finite element simulation on a very fine grid. So I just want to show one result for this specific topic. And what I have here is what you see in these graphs is the acceleration for 1 unit cell. And I think we picked the central unit cell. Here you see the acceleration in X, here at the bottom, the acceleration in Y. And the first column is without the constraint, the second column is with the constraint. It's important to point out, I want to point out that these simulations go beyond the training time. So we're simulating past the training time, but also we're using different boundary conditions than the ones compared to the ones that were used for training, because we want to make sure that the kernel only embeds material properties and is not, and it's independent of boundary conditions, forcing terms, and any other input to the problem. All right, so this was an application to elasticity, but what I really want to talk about is how we apply this technique to bridging the molecular scale and the continuum scale. And we just submitted this paper, and I'm just waiting for Sandia approval to upload it on arXiv. Let me give you some background. This is part of an ongoing LDRD project where we're looking at molecular dynamics as a tool for designing new materials. But in particular, what we're interested in is in testing materials. And the goal is to improve their reliability and performance. When we want to test the materials, however, we cannot use molecular dynamics. We need continuum models that act at larger scales. So based on what I said at the beginning, we need to upscale MD to the continuum scale. When we need to upscale MD to the continuum scale, non-local models or integral models really seem to be the best choice. 3 reasons, but in my next slide, I'll make that clearer. First, they can treat discontinuities. Solutions don't have to be regular. They're compatible with the molecular scale, and they can capture multi-scale behavior because they embed length scales in their definition. We have this capability gap that I mentioned, which is we need to identify the kernel of any non-local model that we want to use. And so we use our recipe. We start from MD data, and then we apply our recipe where we combine physics, non-local calculus, and machine learning, or basically optimization. So I'll be brief here. All I want to say in this slide is that when we coarse grain or upscale or smooth, let's say, molecular dynamics displacement, we can show that the upscaled model is a non-local equation. So I'm going to start from an assembly of interacting particles, and my goal is to go from the particles to a continuum model. We have forces acting between particles and forces acting on the particles, external forces. And what I'm going to do to get to my continuum model is to introduce a smoothing function that has a compact support inside a ball and has some normalization properties. And I'm going to translate all my variables in smoothed variables like this. And then by keeping in mind Newton's law, we combine all these ingredients and we end up with an integral equation. And in the paper, this is done way more carefully. Of course, we end up with this integral equation, but what's the best f? So our goal now is to identify the best non-local constitutive law. I'm gonna recall the operator learning algorithm and I'm gonna extend it to this specific case. Once again, the goal is to learn the best kernel K. Since we are looking at material properties, we're gonna look at operators that are a little bit more complex than the non-local Laplacian, and in particular, we're gonna look at the linear peridynamic solid operator. I'm gonna say a little more about this operator. The important thing here is that this operator has in its definition material properties such as Poisson's ratio and Young's modulus. And it can treat a broader spectrum of material behavior compared to the non-local Laplacian, also known as bond-based model for mechanics. The procedure is the same. We start from ND measurements, ND displacements, and we have pairs of displacements and external forces. And we approximate, once again, the kernel with a surrogate. And once again, it's a linear combination of basis functions. However, we are going to slightly change the definition of the kernel in the sense that we're going to add a fractional term. If you remember the fractional operator that I introduced at the beginning, we had a singularity in the kernel. And the singularity, the intensity or the strength of that singularity is determined by the fractional order alpha. We noticed that having a tunable singularity really makes the predictions more accurate. And so alpha is going to be a tunable parameters together with the sign changing coefficients, meaning that the coefficients are allowed to have different signs. They don't have to be positive for the same reasons that I explained earlier. And then we minimize the residual. And in this case, just keep in mind that this is a more complex operator that also depends on the Poisson ratio and the Young's modulus. And we have an elliptic equation because even though MD is in time, we're just going to look at the last snapshot. So what we're going to minimize is an elliptic equation. Solvability constraints in this case are definitely, they're way more involved. And the reason is that the linear peridynamic solid model is a much more complex model compared to the classical non-local Laplacian. And there is no theory in the literature for well-posedness of sign-changing kernels. And so what we did in our case was simply and I'm just going to describe this in words because I don't want to get into the theorem, but we're going to prescribe discrete IMSUP conditions for this system. And those are going to be our solvability constraint for the operator regression algorithm. And this is just a summary of what I just said, but once again, I don't think this is super relevant. The important thing is that we still have some solvability constraints coming from non-local theory that are going to guarantee that even though our kernel is sign-changing, we're going to have a well-posed problem. Now, let me describe a little bit the material that we are considering and the data set that we're considering. We are looking at single-layer graphene. Graphene is a very resistant material characterized by a negative Poisson ratio. This is an example of a training sample that we use. This is generated with Tersov potential. Stuart Sealing in our team took care of the MD simulations. These are at fixed temperature, and we tested both 0 temperature, so a perfect crystal, and 300K temperature. And the variability in the training data set is given by the loading, basically, by the forcing term. And they all look, they're all different, but they all look pretty much like this. Of course, we want to make sure that the optimal kernel gives good results, even when tested in circumstances that are different from the ones that were used for training. And so we pick a different loading, and we generate new samples that we're going to use for validation. And I have other samples, and I'm going to talk about them later. This is just to give you an idea of the outcome of this algorithm. The kernels very often have this structure. This is the kernel as a function of the distance. So the kernel is radial. So we are only reporting the kernel as a function of the distance. And as you can see, it's negative. And this is really important. I don't have the results in this presentation, but if we don't allow the kernel to be sign changing, we definitely do not get accurate solutions. So this is really important. These are the optimal Young modulus, Poisson ratio, and the good news is that it's consistent with experiments in the theory, in the literature. And here I just want to say a couple of, just spend a couple of words on how we find the optimal parameters. So this is far from being a sophisticated bi-level optimization technique, but basically what we're doing here is to have an outer optimization loop where we find the best horizon that determines the extent of the non-local interactions and the best number of basis functions. So the number of Bernstein polynomials that we're going to use. And in the inner loop, we find the coefficients of the kernel, the Young's modulus, Poisson ratio, and the fractional order. The metrics of accuracy that we're going to use are either the evaluation of the residual of the equation, and this is the one over the training set, or the accuracy of the solution. So this is the our operator with the optimal kernel, and we compare it with the data that we have, again, over the training set. Same measures can be defined for the sampling set. And here I'm highlighting the selections, basically, of the best M and delta at different temperatures. So this is my last example when it comes to MD. And what we do here, I'm just reporting for reference an example of training sample that we used. The testing sample in this case not only has a different forcing term, So here the loading, so these Fs are supposed to be Bs. Apologies. So these are Bs. The forcing term is 0 inside the domain, and it's non-zero outside the domain. And the geometry is completely different, which is probably the most striking difference between the two samples. So this is a comparison between the data, process data, and our solution, which is 9% accurate. And here we use the kernel that was generated by using this type of training samples. And I think what this example is showing is that the kernel truly embeds only the material properties. Clearly, it wouldn't work as well if with something that is not graphene. So the kernel represents graphene in some sense. So I can basically summarize this first part of the talk in what I just said in my last slide about transfer learning. The optimal non-local model embeds material properties. And the optimal kernel is able to work well in settings that are, I would say, substantially different than the ones used in the training phase. Something that I didn't show, but that is in the preprint and that we are still working on, is a hybrid technique to make sure that the kernel is also resolution independent. So it doesn't matter whether we use the kernel on the same grid used for training or on a different grid, we're still gonna get something that is accurate. And the key is the fact that we're looking at a continuous model. Right now, we're working on damage, which is a much more complicated problem. It requires different models, different settings, and certainly different constraints. So this is probably gonna take us a while. To conclude this part on homogenization, I just want to mention that the same technique was used for wave propagation through heterogeneous materials. So here, instead of using a classical wave equation, we use a non-local wave equation to describe propagation through heterogeneous materials. And here, what really made the difference are some physics constraint on the group wave velocity. How many minutes do I have? Are you still there?
Sorry, my computer is slow. I mean, you have plenty of time. Right now it's 7, but yeah, I mean.
Okay. Yeah. Just to have an idea. Yeah. So this is not completely disconnected to what I just presented. And actually, in this second part, I want to show you how we use these kernel learning tools to develop optimal neural network architectures. We refer to them as nonlocal kernel networks because we are learning kernels in some sense. And I just want to add that there's a person, Tian Gao, that I didn't mention at the beginning, but that contributed to this work. So since this is quite a jump, I'm going to pause for a second and let's forget for a second about non-local operators, and I'm going to give you some context. We're looking at neural networks, and in particular, I want to focus on ResNets. And I'm reporting here maybe the simplest form of a ResNet update. We have the increment. H is the value at every layer of the neural network. T represents the layer, and we have the usual affine transformation within the activation function that defines the increment. So the reason why I have a delta T here is because it's well known by now that we can look at ResNets as Euler discretizations. And if we divide this equality by delta T, we recognize an Euler discretization. And as we let the delta T go to 0, we end up with an ordinary differential equation. And that's why these networks are referred to as neural ODEs. So what we like about neural ODEs is that they're continuous. I mean, we're mathematicians, so we like seeing equations, and we like using rigorous analysis and establish numerical techniques. And we can use standard optimization techniques developed for ODEs. So these are features that we like about this continuum model and that we would like to keep in our network. We're still going to work with ResNet, but I'm going to add another feature on top of continuity and interpretability as an ODE, another feature that we would like to have. So let me mention why we want this feature. So as in the previous part of the presentation, we have material design and testing in mind. And in particular, we're thinking of image classification in the context of materials. And image classification can be used for detecting anomalies, detecting signatures of failure, and things like this. So with the image classification task in mind, we're looking at we would like to have a network that is resolution independent. And also, since we know that networks like convolutional neural networks or graph neural networks that take into account long-range interactions in the feature space, meaning in the node space, we would also like to have that feature. So long-range interactions in the nodes, in the set of nodes. This is a cartoon of what I just said, and being resolution independent is something that can be achieved by making the set of nodes a continuum set. And this kind of screams non-local models in some sense. So what we're going to do, instead of having the F that I had in my previous slide for the ResNet, we're going to use an integral operator. Clearly, we're not the first people we're not the first one to look at neural networks with the presence of an integral operator. So I'm gonna recall two important techniques, two important architectures in the literature, and I'm gonna start from them to design our own architecture. So this is the graph kernel network introduced by Lee. Andrew Stewart at Caltech gave several talks about this type of approach. So here we have an original, like the ResNet block. And what we have here is that, so this is an increment, and this is how it's defined. D is the set of nodes, so it's a continuum set of nodes. X is the variable that determines the node, and T is the layer in some sense in this interpretation. K is a kernel. B is the input, so the kernel may even depend on the input. It doesn't necessarily, so in some of their tests, it doesn't. And K is itself a network. So K is a shallow neural network that can be learned while learning all the other parameters. And in particular, the parameters that can be learned are R, C, and the weights and biases of this network. So these are some good and bad points of this network. Unless sigma is the identity, it's hard to establish a direct connection between this network update and a PDE or an ODE. Another bad point is that in the limit of deep layers, this network may become unstable, or at least the accuracy stagnates. What's nice is that it's very descriptive because K is not fixed. K is something that we learn as we go. And another important thing, which is one of the things that we like the most about this network, is that optimal parameters are resolution independent because we are at the continuous level. Then we have another network that is also non-local at the discrete level in some sense. So in this case, this network is discrete, so it's not a continuous, it's not defined as a continuous update. What we have here is that the increment is defined as, once again, non-local interactions. So here we have a kernel that connects two nodes. And what we have here is that this kernel is fixed. I'm reporting the continuous counterpart of this network because it's important to understand the connections between the two. So in this paper, They didn't look at the continuous network. They didn't implement the continuous network, but they simply looked at the discrete one. So in this case, it's harder. You cannot really handle different resolutions because you're looking at a discrete network. K is fixed, so it's probably less descriptive than the previous one, but it's stable as the number of layers increases. And what makes it stable is the presence of this extra term, the HJ. I'm sorry, the HI. So it's the difference that makes it stable. And I'm going to say more about this, and I'm going to say why this becomes stable. And also, it can be analyzed as a discrete non-local equation, because this is truly the discretization of a non-local Laplacian. Just an additional good property of the bottom one is that, as opposed to the previous one, we can handle different resolutions because it's formulated at a continuous level. So now let me get to our network, where we try to combine the good aspects of both. And so we have the network update here, and this network update is defined with an integral operator where we have the difference. So we're trying to mimic this network, so the one that is stable, and we're adding some what we're going to call reaction terms and some forcing terms. Also, K is going to be a shallow neural network, and R is going to be a neural network to increase the descriptive power of this network. But note that both the kernel and R are not time dependent. As I said earlier, D is the continuum set of nodes. At times, we will consider the whole set of nodes, but sometimes we will just consider a ball surrounding a point just for efficiency purposes. This is a summary for our network. We're going to use it on both PDE-learning tasks, which is what graph kernel networks were developed for, and image classification, which is what the non-local networks were designed for. The important feature that we want is being resolution independent and being stable in the limit of deep networks. And this is possible because we can show that the network is stable. Together with the stability in the limit of deep networks, I want to introduce this technique that we use, and I'm going to show you some results right away because I'm not going to go over this specific technique. We use a shallow to deep training, which means that we can initialize deeper and deeper networks by using the result coming from the more shallow network. And this is possible in our specific case because our networks here, our network parameters do not depend on time. But the shallow to deep training can be done for any stable network just by interpolating the optimal parameters over the layers and by using them as initial guesses. And this is exactly what we did. When we have two layers, we have basically random initialization for both. And what we do as we increase the number of layers is to use the optimal solution at the previous number of layers as initialization. And as you can see, the training is much faster. We start from a much lower loss value. This is the training loss. All right, just one word on stability. I'm going to consider the scalar case so that there's really a resemblance with what I presented in the previous part of my talk. So what you can recognize here is a non-local Laplacian. And if we call these LK, as I did in the previous part of my talk, and we divide everything by delta t, here we have an Euler discretization, a non-local diffusion, a reaction term, and a forcing term. And as we let delta t go to 0, we have a parabolic non-local equation. So this is a non-local diffusion equation, and we can use the unified or non-local calculus to analyze it. And by using the non-local calculus, we can find sufficient conditions such that this is stable. And this is basically why we can guarantee stability. All right. I don't have a lot of examples, so I'll try to, I think I'm going over time. So first, we consider PDE-learning. In this specific case, we pick exactly the same tests that were in the graph kernel network paper. So we have a PDE where the differential operator is characterized by a parameter b, which is the input. And here's our PDE. The goal is, given some training set, B, F, and U, we want to learn a map from the input to the output that is resolution independent. So it's independent of the discretization side. This is just a technicality on how we set the initial and last layer of the network. The proof of concept result is Poisson's equation, where the operator is the second derivative, and B, the coefficient of the operator is 1. This is how we generate solutions. We're basically using manufactured solutions. And here's a comparison in terms of training error and testing error between graph kernel networks and non-local kernel networks. And we are observing exactly what was predicted by the theory, which is the graph kernel network seemed to stagnate as we increase the number of layers. So each column indicates the number of layers. And we have both the train and test error. And as you can see, instead, the graph kernel network, the non-local kernel network is stable. To further confirm the stability, we also compute the eigenvalues of the operator, which show the minimum and maximum as a function of the layers, the number of layers, which confirm the coercivity of this operator, which guarantees stability. We tested it on Darcy's flow, 2D Darcy's flow. In this case, the input is the permeability, which is a two-valued piecewise constant function, which is generated randomly. And once again, we do the same test, and this is also in the graph kernel network paper. We consider different resolutions and different number of layers. And we observe the same thing. While graph kernel networks stagnate, our network keeps improving. And this confirms once again stability. But here's another test that shows the fact that this network is resolution independent. And what we have here is, so the first S is the resolution during training, and the second S prime is the resolution for testing. And while for low layers, we see that graph kernel networks do, I would say, almost an equally good job. They're actually better. In the limit of deep layers, we definitely do a better job with the same resolution and with the cross-resolution test. NA, by the way, just means that we didn't have enough memory and we had to give up. All right, I'm just going to conclude with image classification. I truly have 2 slides. These are the data sets that we consider. The first one was much simpler to train. And what we have here is a comparison with CNN, non-local neural networks, the discrete ones, and our network. And so here we have images. Here we train on fine images. Here we train on coarse images, and we validate either on fine or on coarse, and same here. So while CNNs are always the most accurate on the same resolution in terms of validation, they definitely do not, they don't do a good job in cross-resolution tasks, while non-local kernel networks do. So here block just means layers. In the non-local network community, they're apparently called blocks. And R simply means that we don't look at the whole set of nodes, but we only take the integral over a ball of radius 3. And these are the results for the CIFAR 10 data set. And here we compare CNN once again with the non-local neural network and the non-local kernel network. Same resolution, finer resolution, coarser resolution. And it looks like this network always gives better results. All right, I think I talked for too long. So I'm gonna thank you for your attention, for staying with me until now, and I'm happy to take any questions.
Thank you so much, Marta, for the interesting talk and wonderful talk. It was very educational for me because I was not familiar with the non-local the formulation at all, but it was good exposure for me. Okay, let's have a Q&A sessions. Okay, let me look at the chat room. I do see a question from Gavin. He's asking, thanks, Marta. Can you explain the shallow to deep training again? Is there a reference for that procedure?
Yes, absolutely. I should have put it, actually. It's a work by Eldad Haber and Lars Rutotto. It's about multi-scale convolutional neural networks. I'll make sure I send the reference for this. So basically here, sorry, probably I went too fast on this. What we can do is learn the optimal parameters for a first number of layers. Let's say we learn the optimal parameters when we have 4 layers. And then once we get to convergence, we take the optimal parameters and we use that solution as an initial guess for the next training with 8 layers. So in our case, this technique is incredibly easy simply because our kernel and R do not depend on time. So the layers represent the time. So for us, we can simply pick the optimal solution and stick it in there, and there's no problem. However, when you have optimal parameters that depend on time, that means that when you train on 4 layers, you're going to have optimal parameters for 4 layers. But if your network is stable, what you can do is to take those 4-layer parameters and interpolate them and project them on the 8 layers. And so you have a new initial guess that comes from interpolating or evaluating your 4 optimal parameters on the 8 layers network. And you use that as an initial guess, and your loss function is definitely going to start from a much lower value, and training is much easier, is much faster.
Oh, thank you, Marta. So I don't know, I had a related question about that. So when you increase the number of layers from going from shallow to deep, do you keep the number of hidden nodes when you increase the layers? How is there?
I keep the number of nodes the same. Is that the question? Yeah. Yes, we do.
The hidden nodes. Oh, you do.
Yes,
okay.
Yes. But you don't have to, right? Because it's all continuous. So if you want to change it, you can. So if, let's say, you feel like you cannot afford it, you cannot afford the same number that you had before, you could change it in principle. We didn't, but there is nothing that stops you from doing that.
Yeah. Okay. So the other numerical example needs to be done. If you change the number of hidden nodes, how the accuracy of the train loss change. I'm hearing the echo again of my voice.
Is it better? I just removed my headphones.
Oh, I see. I'm hearing. I'm hearing the echo.
Is it better now? Sometimes.
Hello. Yeah, I don't hear it anymore. Okay, that's great. Okay. Right. Is there any other questions? Okay. Well, I have a couple of more. Yeah, this talk is recorded, and whenever it is available, I will let everyone know. Okay, so for the first part of the talk, you mentioned that you're aiming for the application where kernel functions are not known in non-local formulation, right?
Yeah.
And only the data is available, right?
Right.
So what are those applications? Is the paradigms you have shown in the presentation?
Yeah, so we use so paradynamics was not designed for molecular dynamics, right? So we're using a paradynamic model that is usually used for modeling fracture in some sense. But we found that this is at least in this case, is a good model to describe coarse-grained molecular dynamics displacements. This model is not going to work with damage. We have to change this model. We have to embed a damage tracking function. So that's what we're working on right now. Now, I started by mentioning the subsurface example. So this is an example where the kernel is given. However, it's given. People have been using this kernel for years. However, fractional models are incredibly expensive. And sometimes they, you may not want to go with this form. You may want to go with, for example, an exponent that depends on x. And so the learning problem comes back. What's the best, not only what's the best s as a scalar, but or as a constant, but what's the best s of x, so function that gives you the order. But even going beyond this, we're now looking at not using fractional operators. So what we're working on now is to find, because they're really expensive, because you have to integrate over infinite domains, and definitely fractional discretization has made like gigantic steps forward, but this is still expensive. I mean, you still have an infinite domain. So what we're looking at is truncated kernels. So we want to reduce this domain of integration, but as soon as you do that, you may lose something, and so you have to compensate. And so that means that you have to find a better kernel. And so we're after an optimal kernel for anomalous transport.
I see. So even for the application where the kernel is known, the application of kernel can be very expensive. So alternative might be beneficial. Okay.
Yes.
Is the all the examples seems to be the elliptic equations. By the way, can it be applied to the hyperbolic?
Yeah. I didn't want to use too much of your time, but so so I showed one at the beginning. So this is time dependent. It's a non-local counterpart of elasticity. And here we have wave propagation, and the equation is a non-local wave equation. So basically you have second derivative in time. And of course it's more expensive because in your loss function, you have to consider all the time steps. In particular, what made this really expensive was that minimizing the residual of the equation was not good enough. We were not getting good results. And so what we had to do here was to go back to the counterpart of PDE constrained optimization, basically, where we minimize the difference between data and displacement, subject to the non-local wave equation. It performs well. It's more expensive than the one that I presented previously, but the idea is the same. Bernstein polynomials for the kernel, and the loss function now has time data as well. It's a time series as well, the data.
I see. Okay, so my another question is for the molecular dynamic, the problems. One of the advantages of using the non-local method was you can introduce the discontinuous the basis for the kernel, for example.
Yeah, but it's also the computational saving. You reduce the number of degrees of freedom by a lot because your non-local grid is much coarser than MD. So the number of degrees of freedom really cut.
Right. So regarding that, my first question is, so in some sense, you've been using the Bernstein basis function for the kernel all the time.
Yes.
But technically, you could use other discontinuous basis function, right?
Absolutely, yeah. You can use. So I can tell you why we use them. Especially in our first work, we wanted to do analysis, and these are compatibly supported positive functions. And dealing with improving stuff when you have a positive function, when you know the sign of your function, is much, much easier. So that's the main reason for which we pick them. But as long as you make sure that you prescribe the good constraints, meaning well-posedness constraint, you can even put a neural network there. But so in our very first work, we had a convex problem. I mean, it was a nice, with Bernstein polynomials, it was a very nice problem. As soon as you put a neural network, it's a mess, right? Proving things and even the optimization. So I guess our approach is, if we don't need it, we don't use it.
Yeah, I totally agree.
It's just we're lazy. Let's put it this way. No, I mean, I'm joking. It's just that if you get results that are accurate enough, there's no need to make the problem more complex.
Yeah. I mean, well, you said it, you're joking, but I'm in some sense I'm not joking. You know, I'm in the community of the I'm actively doing the research on the surrogate modeling or reduced order modeling. There are a lot of neural network, approach tries to, the building the surrogate model in there. But which gives you great representability because it's introducing nonlinear representation of your solution compared to the traditional, linear subspace solution representation. But in theory, it's not supported richly, those neural network thingy. And also the training of those neural net is
exactly.
It's a lot more expensive and a lot more trial and error has to be done.
Absolutely.
While the linear subspace, just the solution representation, it's theory, it's backed by theory very rigorously, and also the training is very cheap. And my philosophy also, aligns with yours. If the linear subspace and the simpler method works well, then do not move on to the neural net.
Exactly.
All right. Okay. So my next question is, for molecular dynamics, how is the data generated? It's generated by the simulation I do.
Yeah, it's an MD. It's the code is a Sandia code, which actually I believe is not available. Like it's a code developed initially for peridynamics, so for non-local, but that was adapted to MD, and we pick a specific potential for MD, the tensor potential, and these are just plain MD simulations. Stuart Sealing performed them.
I see. Okay. Thank you so much, Marta, to answering
Thank you
all
for
of
having
my
me.
questions. I don't see any more questions from the chat room, so I'm assuming that no more questions for Marta. Don't be shy though. If you do have a question, please speak. If not, we will wrap it up here. Thank you so much, Marta, for the wonderful talk and
thanks a lot for having me. It was a pleasure.
Yeah, it was wonderful. I mean, today is the day I will be more interested in non-local approach.
Fantastic. I'm really happy to hear that.
Yeah. And for everyone else, I hope this is the initialization of the future collaboration with Marta. And Marta is doing wonderful work.
Thank you.
If there is a chance for the collaboration, that will be awesome.
Yeah, we're always very open for collaboration.
Okay. Wonderful. With that, okay, thank you again, Marta, and thank you everyone else who joined us. And I believe the next DDPS seminar is again next week. So please stay tuned for the announcements. Okay. Thank you, Marta, and thank you everyone.
Bye.
Okay, bye.